Okay, good. We'll now move on to the next speaker in the session. And I'm just checking my crib sheet. It's Mariella Minder, yes, from the University of Cambridge and Toshiba Research. The title of her talk, hi Mariella, good.
Hello. Hi, John.
Is Advances in Experimental Twin Field Quantum Key Distribution. This is a 20-minute talk with 5 minutes questions. What we've been asked you to prepare. I'll give you a wave when it's at 5 minutes.
Okay, perfect. Let me see. Okay, cool. Can you see my talk? Perfect. Okay. So hello, everyone. I am Mariella. I'm a PhD student at the University of Cambridge and at Toshiba Research Europe. And today my virtual talk will be about the advances in twin-field quantum key distribution. So I have structured my talk as follows. I will start by explaining the motivation behind research into twin-field QKD. Then I will introduce the initial scheme, the original proposal, and I will continue with some of the variations that have occurred since. And then finally, I will talk about experimental twin-field QKD. What is the main challenge and what advances have we seen in that aspect? So to explain the benefit of twin-field QKD, we can see this slide, which shows the state of the art for quantum key distribution and for measurement device independent quantum key distribution. And you can see that all of these points, all the really good results, they follow this specific trend. And it seems like there is a very big region of this graph that we are not able to reach. So what we would like to do is maybe to give a new trend to our QKD points and somehow be able to populate the gray area here until at some point we're able to perform really well and reach the sweet spot that is like this red triangle here. And in fact, the fact that these points have this kind of trend is not a coincidence, and it's because they are theoretically bound by the secret key capacity, which I denoted here as SKC0, and it is this line right here. And the origin of SKC is just because of the transmissivity that you have in a certain QKD channel. So as you have fiber or free space connecting Alice and Bob, then it means that these will have a certain transmission or transmissivity, eta, and then depending on the loss coefficient of the channel, it means that the SKC is kind of giving you the maximum rate that you could reach at every channel loss, and also is giving you the maximum channel loss after which your photons are attenuated and hence you cannot distill a key. So with QKD, we cannot get longer channels than this, so we cannot overcome the SKC0. And we also cannot get untrusted nodes, which is something that is very desirable if we want to implement QKD networks. However, it is a very implementable protocol. We have people have researched it a lot. So as you can see, there are many results. So still very useful. And moving on to the blue points, which are measurement device independent QKD, these seem to follow exactly the same trend. So they are still bounded by the secret key capacity 0, which means that although we have 2 transmitters, in MDI QKD, the receiver, which can be an untrusted node, performs a Bell state measurement. And because of the need of the Bell state measurement, it means we also need coincidence counts. So although we have this architecture, we're not able to overcome the secret key capacity. However, with implementing MDI QKD, we gain untrusted nodes, and it is still an implementable protocol, so it is practical. And the way we could actually perform better is if we had a QKD system with 1 repeater, or with many repeaters, actually. But in the case of a 1 repeater, then we have this line here, which is the secret key capacity for 1 repeater in the system. And as you can see, it definitely has a different trend than SKC0. And the difference is that now we depend rather on the transmissivity, but we depend on the square root of the transmissivity. So this means that a repeater is going to give us the chance to populate this region here with points. It also gives us an untrusted node. However, we are still not very close to having a really good system with a repeater, although we're getting closer given the recent advances with memory enhanced QKD. So twin-field QKD is giving us a solution to this problem, a solution that is readily implementable. Twin-field QKD is an efficient MDI QKD protocol, so it means that it's still measurement device independent. It still uses a 3-node architecture. However, because it does not utilize a Bell state measurement, it means that from single counts, so from single clicks on the detector, we can still distill our key. And because of this, we get the security bound for TFQKD, which is this red line here, which is parallel to the secret key capacity for one repeater. And this means that the key rate for twin-field QKD is proportional to the square root of the transmissivity. So twin-field QKD is giving us longer channels, it is giving us untrusted nodes, and it's also currently implementable with the technology we have. So this is why we're so motivated to look into this protocol. So by implementing twin-field QKD, we should be able to populate this region here over the secret key capacity, but also this region below the secret key capacity, which we are not able to fill with MDI and QKD because these are protocol-specific bounds that lie in this region here, so because of the security analysis. So twin-field QKD takes really good characteristics from other QKD architectures. So from QKD, it takes a single photon interference. However, it maintains the untrusted nodes that we see in MDI QKD, and then it gives us a similar result to repeaters where we have the square root being of the transmissivity being proportional to the key rate. So how is this protocol performed? The way that TFQKD is performed is we use phase encoding to encode our bits, and then you can use 2 bases or you can use 1. And then on top of that, you implement your decoy states because you're going to use weak coherent pulses. And then the crucial step is phase randomization. In this step, the 2 users, Alice and Bob, will each independently choose a random global phase to encode on their pulses. And this can be any value within 0 and 2 pi. So they have an infinite number of value that they can use. And then during sifting, they will sift, of course, their bases and their intensities like we usually do. But now they also have to sift the base slice of the randomization value that they have used. So what this means is that they can never have their encoded, so their randomized phases to match exactly. So they have to decide on a discretization of this space circle, and then they have to announce the phase slice that their encoding belongs in so that they have a chance of them matching rather than sending infinite pulses to have a matching chance. This also means that if you discretize the circle in m slices, your key rate will also be proportional to 1/m. So this is the penalty we pay for TFQKD. Now, since the initial proposal, there have been many other TFQKD variations, and these can be divided in 3 categories. So there are the ones that look like the initial scheme. They are performed the same. They need the same requirements experimentally. And then the first category is protocols that do not require phase post-selection or NPP TFQKD, in which protocols you can separate the code and your test bases. And the important part here is that in the code basis, you do not perform any phase randomization, but solely the phase encoding. And then you keep the phase randomization for the test basis. And by test basis, I mean the basis that is going to be used for decoy state analysis or estimating the single photon error rates, etc. So the fact that we do not phase randomize the code basis means that we do not need to sift the global phase randomization value. We can still extract the keys because without it. And then it also means that because of this, our rate will not be scaling with 1/m, so that penalty is removed. And hence we can overcome the secret key capacity at lower losses, which is a really good advantage. Now looking at the third category, which are the send-not-send type protocols or SNS. These protocols, again, they separate code and test. The test basis is performed just like TFQKD, so as you see it here. And then for the code basis, the phase encoding is replaced with intensity encoding. So Alice and Bob have a probability of sending a pulse, and this probability is very small in the first proposal. So in the basic protocol, this should be around 5% maybe, or even less. So whenever Alice sends a pulse and there is a successful measurement at Charlie at the detector station, she will encode a 1, and whenever she doesn't, she will encode a 0. And then Bob will do the same. He will save a 1 when he doesn't send, he will save a 0 when he does send a pulse. So you can see from this graph that whenever they both decided to send whenever they both decided not to send, they will get errors in their bit string, while if only one of them has sent the pulse, then they will get matching bits. And because the probability of both of them sending is very tiny, and because both of them not sending might be a big probability, but it's only governed by dark counts, then you end up with decent errors in the protocol. And the very good thing about send not send type of protocols is the fact that they're very tolerant to phase misalignment errors. So phase is a very big problem for Tfqt. It's something I will talk about in the next few slides. The fact that we are intensity encoding our code bases is very advantageous in that sense, that we can have a little bit more noise in the phase and still extract a key. So SNS can tolerate over 30% of phase misalignment error. The other very interesting thing about SNS is the fact that if you implement the two-way classical communication post-processing method, which is this kind of bitwise parity pairing sifting of the sifted key, so it's a second sifting stage, you can get great results, something that is not very common amongst QKD protocols. So you can get an extra 20 dB of loss tolerance. And as you can see here, this is like this is really good because we already can reach very high distances, and now we're getting an extra 20 dB just by doing some post-processing. So my point at looking at all of these variations is to see the fact that Twin-field QKD is a quite adaptable protocol. So we have variations that are better for lower loss, variations that are better for higher loss. And then depending on your implementation, so maybe your channel is a bit more noisy, then you can use a more error tolerant protocol like the SNS. Or if it's not very easy to do phase post selection, then maybe you want to implement the NPP protocols. So it is a very adaptable protocol. But the main challenge in this protocol, so it is very efficient, but this comes at a cost. It is the phase. So the fact that we're playing with phase and the fact that we have very long channels. So we are trying to encode these global random phases on the users, and these do this independently. And then they have to sift this global phase randomization at the end. So they have to announce a phase slice. And their phase slices have to match in the sense that if Bob announces this slice, then this slice is the same as Bob Alice's slide. So this means that they have to start with the same phase. So you definitely need a phase reference to be distributed to the two users. So the Alice and Bob must be phase locked at very long distances. So let's say 500 or 600 kilometers. And then on top of that, phase reconstruction is also something that is definitely required for Tfqt. So even if we do successfully phase lock the sources, then when they send their phase encoded pulses to travel through 500 kilometers of fiber, they will be experiencing some vibration or thermal changes, and these will in turn make some differences in the length of the fiber, which end up as a phase noise. So we end up with a phase drift rate that at 550 kilometers, as you see in this graph, has an average of 6 rads per millisecond. So it's a huge drift, and we haven't seen these drifts stabilized before. So essentially, the initial phase that you have encoded is completely scrambled by the end. So you have to have a way to reconstruct the phase when Alice and Bob are interfering. However, even though it is quite a challenging protocol, we have seen great results in the past 2 years from different groups. So the things we see in this graph, so all the colored points are Tfqt results. And it is clear to see that we get much larger secret key rates than we do with MDI QKD, although this still keeps untrusted nodes in the system. Definitely 20 dB more tolerant to loss. Distances such as 509 kilometers have been reached in fiber, which are the record distances for quantum communications at the moment. And also we see the same scaling as a single repeater secret key capacity bound, so we can overcome the repeaterless bound, which is really nice. So to go through the trends a little bit in the experimental implementations of Tfqt, I will start with this experiment, which is our experiment. And this was the first implementation for twin-field QKD. And how we decided to approach the challenges of Tfqt is we decided to first phase lock our sources with a heterodyne optical phase lock loop. So use an extra duty fiber that is carrying the locking light. And this is our OPLL. I will go through OPLLs a bit more later on. And we also used an active phase stabilization. So we used some reference pulses that were time multiplexed with our QKD pulses, and then we used them to calculate from their SPD detection, use them to calculate a correction signal to send to a phase modulator and actively correct the phase. The other thing we did is we wanted to represent all the three categories of protocols, so we tried to implement all three. However, we did keep short channels. So we used only 100 meters of fiber in the channels, and then we simulated longer channels by just increasing the attenuation using variable optical attenuators. And the reason we did this is because obviously we wanted to avoid having rads per millisecond drift and rather deal with rads per second drift, which was already challenging. So what we showed with this paper is that, first of all, this was the first quantum system to show a repeating behavior. If you look at the top left graph right here, then you can see the gain versus channel loss for our system, which are the red points right here, and the green points are for standard QKD. And as you can see, for every channel loss, we get double the gain if you implement TFQKD. So this was a really nice achievement. And then moving on to the right graph, we did implement the three protocols successfully, and we were able to prove the feasibility of TFQKD and its variants, and we were able to surpass the secret key capacity with all the protocols. The maximum loss that we achieved was 83 dB for information theoretic secure protocols and a bit over 90 for a protocol that is secure against collective attacks. So since we have seen some other alternative approaches to this phase reconstruction problem, so some people have tried to do the active stabilization, and to go a little bit more into detail on how this works is essentially you use some unmodulated reference pulses that are time multiplexed with your QKD pulses. And if you have very long channels, so a faster drift, then you need to definitely put some intensity modulation so that you have enough sample at your single photon detector to use it as a feedback signal. So what you do is at the single photon detector, you will observe the interference fringes of these reference pulses, and then you can map every intensity to a phase. So what you want is essentially a locking condition to which you want to push your intensity. So you can, let's say you're here, you translate this into a phase, and then you calculate how much voltage you need, sorry, on a phase modulator to push this point to your locking condition. And then you do this continuously, and what you end up with is a very stable low Q-ver when you have the feedback turned on, and just a random drift when the feedback is off. The good thing about this approach is the fact that every pulse is used. So every successful measurement at Charlie will be useful because the pulses are stabilized, so you don't need to waste anything. Also, it is multi-protocol, so it is efficient for all the protocols. There are no penalties for certain protocols. And it is also a technology that could be very useful for repeaters later on. It's good to look into it. And then looking at the alternative approach, which is a post-processing method. So here, reference pulses are still time multiplex with QKD pulses. They can either be longer than QKD pulses, but they definitely need to be brighter. So instead of trying to correct the phase, in this approach, researchers are trying to map the phase. So you look at the interference fringes, you can tell where on the phase circle in which slice Alice and Bob have interfered at Charlie. And then you can either choose to use only pulses that have interfered with pi or 0 phase difference, or you can choose to use a bit more, but then that depends on how much you can handle with error correction and how much error other slices are going to give you. But definitely you will, for example, need to get rid of pulses that have interfered at 90 degrees because the error would just be too big. So most of your key rate essentially comes from this 0 pi condition here. So the benefit is definitely it's a easier, maybe a faster implementation. You don't need to develop the electronics to correct it, and it is a good alternative approach for sure. People have reached 509 kilometers of TFQKD using this method, and the secret key capacity has been surpassed like this. But maybe the drawbacks are the fact that it is not very useful for protocols such as the no-phase post-selection. So if you implement this protocol, then at lower losses, you will have suboptimal performance. And also the fact that you always need to waste some of the signals means that you have a slight penalty in the rates. And this is bigger in certain protocols. So for example, in the SNS, it's not such a big issue, but for other protocols, it is. And moving on to the phase locking issue. Now for phase locking, I feel like there is a clear winner in terms of how to do this. And these are optical phase lock loops. For now, at least, we have seen attempts to do this with optical injection locking. However, using injected light is kind of maybe not secure. So that's why most groups prefer to use OPLLs. And what we do in an optical phase lock loop here, I have put a diagram of our OPLL. So for our proof of principle experiment, what we are doing here is we are interfering Alice and Bob's laser. And Bob's light is modulated by some small amount in frequency. And then we observe on a photodiode the beating signal. And essentially the photodiode acts like a sensitive, phase sensitive detector. So we can use that signal and the local oscillator at Bob to kind of create a feedback loop that is given to Bob's laser, and then he can follow the fluctuations of Alice. So they're always locked in phase. And this is the result that we had obtained. So we were able to lock to a leftover error of 5 degrees, which was a really good result. And you can see this from the high extinction ratio of this peak. So for longer distances, such techniques must be combined with with other techniques that can make the line width of the laser sources much smaller. So for example, the pound river hole, where you use stable cavities to lock your lasers, and you end up with 1 Hertz line width, which is really good if you're gonna make these pulses travel through 500 kilometers of fiber. So we have seen this here. People have achieved the 509 result using this method. And the good thing about this is that it is definitely secure. We know that it is secure. The OPLL light is separate, so it does not interfere at all with our QKD light. It is quite an established technique. It has been used in classical communications for many years. And also it gives us high quality phase locking, so it is definitely enough for us to perform twin field QKD. So overall, with this talk, I wanted to show the importance of twin field QKD as a protocol. It's a protocol that shows a repeating behavior, so it enables us to achieve record distances for the first time currently. It also has untrusted nodes, which it means that it is a protocol that is very ideal for networks, and it is readily implementable. The fact that we have multiple variants, it means that it is a protocol that can be adapted to different practical conditions. So it can be suitable for many different situations. And experimentally, we have seen some great progress. So the post-process phase reconstruction technique is definitely successful. We've seen it a lot. OPLLs at 509 kilometers do work successfully for twin field QKD. And record distances and losses have been reached, as you can see from this plot right here. Now, what we would still like to see maybe from experimental implementations of TFQKD is an active phase stabilization at long distances. So the longest distance that an active stabilization has been shown is 300 kilometers. And also maybe a higher practicality in the locking system. I mean, using all these EDFAs and the fabric rock cavities and having an extra duty fiber is a complicated situation. So maybe an advance there would also be very nice. And finally, multi-protocol system. So if you have active phase stabilization, then you can also have a multi-protocol system. So it would be nice to show a system that can perform better at shorter loss, at lower loss with another protocol, and then better at higher loss because they're using another variant of TFQKD. So that is all from me today. Thank you very much for listening, and I will be very happy to hear your questions.
Thank you, Mariella. Another excellent talk. I'm there are a few questions up here. The top is Jaylan Atkas from Bristol asks a very nice talk. Obviously, TFQKD implies very precise synchronization of the incoming pulses in time. Can you comment on how you do the time synchronization as well as, of course, the phase stabilization?
Yeah, so for time synchronization, I mean, for experiments that we have seen until now, or let's say for experiments that are until 500 kilometers or some 600 kilometers maybe, the time misalignment is slow. So you don't necessarily need an active stabilization yet. However, if you want to make this an automatic system, then definitely you will need to use some electronics to correct for that. But I think for now, so let's say it's in the order of minutes. So for us, for example, we can just be there and correct it manually. So just shift the delays, but you would need to use, yes, a signal that is going to do that automatically if you want to actually implement it in a commercial system.
There's another question popped at the top from Mehul Malik. Do your phase lock loops introduce any device-dependent security loopholes?
Yes, so our initial approach to Tfqt was to use optical injection locking. And optical injection locking was definitely not secure because Eve can play with the light and send some light and do things that we don't want her to do to QKD light. However, when you use an optical phase lock loop, the fact that you're isolating the light and you're using it only for the OPLL means that even if she tampers with it, in the end, what she will introduce is errors in the measurement. So she can shift the phase and like shift the locking. This will translate into error, and she can't actually like do something that is device dependent. Okay.
Okay. And another question, a popular question from Soren Wengarowski. If Alice and Bob are choosing their phase out of M slices in a random way, the overlap of that is 1 over M squared. So he's wondering why you say the key rate scales with 1 over M. There's probably a simple explanation to that.
So it's 1 over M squared.
If you're choosing your phase out of M slices in the 360 degree, 8 degree sections or whatever, Alice chooses one phase with a probability 1 over M, and Bob chooses another phase with a probability of 1 over M. Therefore, their overlap of phases in the right modes is 1 over M squared. I suspect it's 1 over, your scaling goes as 1 over M because all they have to be is pi out of phase, and once you've chosen one, they're all equivalent. You can choose any one, and as long as the other one is pi out of phase,
yes, exactly,
probability,
yeah, exactly. So they don't have to be exactly these. Yes.
So I've answered Soren's question for you.
Yes, thank you.
Sorry. Any more down there in the list? So I think somebody else was saying, is there any side channels created by the active stabilization? So a similar question to Mehul's. Maybe those you can take offline on the Slack session so that we can keep to time. I was very poor at timing earlier on, but I'm catching up a little bit now. So that's great. So I'm going to thank you again, Mariella. Great to hear you talk again. I'm always impressed with this work, and I'll see you in Slack, and we'll go on to the next talk.